Hi, and welcome back. Last time, we introduced calculus of variations, a powerful set of techniques for finding the optimum to various kinds of problems involving functionals, an idea we also introduced in the last lecture. This week, we're going to figure out how that relates to Lagrangian mechanics, a set of ideas that developed after the Newtonian formulation of mechanics, but fundamentally describe the same phenomena. Now, the pathway here is very interesting, so I want to hop into it right away. Before Newton published the Principia, there were many people in the 17th century working to understand various areas of mathematics, one of whom was Christian Huygens, and he's known for many different things, but in particular, he's known for trying to figure out how to make clocks better. This was actually a big thing in the 17th century because trying to keep clocks on time was a difficult engineering problem. Now, grandfather clocks, and more generally, different kinds of pendulum clocks, existed at the time. And one thing that Huygens noticed was that you couldn't keep those clocks on time that easily, and that's for a simple reason. The period of their oscillation depends on how high they swing. Now, when you've worked out pendulum problems before, perhaps in introductory mechanics, you've used the small angle approximation, which suggests that, at least to leading order, the period will be the same no matter what the amplitude is. But it turns out that these higher order corrections, over a long period of time, like the lifetime of a clock, can really lead to a bunch of deviation. So he wondered, what could possibly be the correct shape? And by a mixture of testing and some sort of rudimentary mathematics, Huygens found out that the shape should be a cycloid, the same shape that we talked about last time as being the brachistochrone shape. However, Huygens' proof was not complete, it wasn't perfect. Instead, we would have to wait much longer. In the 1750s, Leonhard Euler and Joseph Louis Lagrange together in a series of papers that they published, or letters, I should say, that they sent back and forth to each other, ended up being able to prove the same statement that I just said, that the curve that allows a pendulum to swing at an equal amount of time, no matter what its amplitude, is a cycloid rather than a circle. However, even though this happened in the 1750s, it would take several more decades and contributions by a number of other mathematicians to sort of make it fully realizable as a theory of mechanics. But eventually, it was realized, mostly by Lagrange himself, that the same kinds of techniques that had been used in this clocks problem were applicable to all kinds of mechanical phenomena. He eventually published this, in a work that's titled in English Analytical Mechanics, in French Mécanique Analytique, in 1789, 101 years after the Principia. So we're talking a lot of time in between. All right, so we've kind of come at the basic principle from this historical angle, but maybe I can be a little bit more specific. We've seen in calculus of variations the basic idea that if we have some kind of a functional, then we can try to make that functional optimal, or in a more general setting, we might just want to find a function which makes that functional stationary. Well, trajectories of particles in Rn are a kind of function. And so it could be the case that we can find some functional on the space of trajectories such that the stationary points are the actual trajectories taken. So let me write that as our goal. Now, for reasons that will become true, or become clear, I should say, later, we're going to call this functional S. So it's going to act on functions from R to Rn, which we'll think of as trajectories. Such that the stationary curve is the trajectory actually taken by a particle. Great. Now, I could present the whole theory to you here, but I actually think that there's a better way to do this. We've gotten a lot of comfort with calculus of variations over the last lecture. We've done a lot of examples so far. So why not just hop in and try and see if we can cook up a functional that works at least for some cases of interest. I'm going to do that on the computer, and then I'll hop back here to explain the theory to you in a little bit.
All right, let's hop right into OneNote and do some examples. The simplest thing that I can think of to start with that isn't super non-trivial is what if we have a system of a mass that's attached to a spring? Maybe I'll put the mass over here. We have this mass on a spring. The mass has mass m, the spring has spring constant k, and 0 equilibrium length. So we know that what we're expecting in this case, in fact, let me just write the diff EQ, is that x, this is in 1D, x double dot times m is equal to kx with a minus sign. Great. Okay, now what can we possibly try to get ourselves this equation from calculus of variations? Well, it's not super obvious, and in fact, it took centuries to figure it out. But let's define two things. First of all, let's define the kinetic energy function of v. So if you have an object with speed v, its kinetic energy will be 1/2 mv squared. We know that. And then we can also define a potential energy function, which will only depend on x. In our case, this is going to be 1/2 kx squared. Now, the idea is to combine these into one object. In our case, this is going to be L, which is a function of two variables. It's a function of x and a function of v. So this is a function from R2 to R, and it's just a regular old function. And it's defined by L of xv is equal to t of v minus u of x. Great. Okay, well, let's try to use this to define a functional, s. So we'll say s of, now let me give a name to the trajectory. I guess I'll call the trajectory u, just to distinguish it from x. Okay, s of u is equal to the integral from t initial to t final of L of u of t, u dot of t. So those are filling the roles of position and velocity, dt. Great. So this is, let me say, a non-obvious guess. Later on in the video, when we go through the theory of all of this, we'll show why this guess makes sense. But for now, let's just see what happens. We've now practiced enough calculus of variations that we kind of know what to do in this case. What we need to do is write out what L is, curly L. Well, if I pull this and this all the way through, I'll get 1/2 m times u dot of t squared minus 1/2 k u of t squared dt. Now let's find the EL equations, or I should say equation in this case, for this system. Great. First I need to take the u derivative. Let me do that first. In this case, u only appears in that second term. So I'll get minus k times u of t. On the other side, I'm going to get d dt times the derivative with respect to u dot, which we see in this case is 1 half, or I should say, sorry, the 2 cancels the 1 half, is just mu dot of t. Now m is a constant, so in the end, this gives me mu double dot of t. And I can rewrite this in a startling way. I have mu double dot of t is equal to minus k u of t. So here's the kicker. U of t is the, or I should say, satisfies the equation from Newton's second law, which is somewhat startling. The question is, does this always work? Let's just, at this point, go ahead and try it for a bunch of different cases. So maybe I'll make sure that to label this example 1, example 2. What if we just had t of v, sorry, let me say, let's do t of v is equal to half mv squared as usual, and u of x is equal to 0. Again, I define L as equal to L of L of x and v is equal to t of v minus u of x. And so my action is s of u is equal to this integral from ti to tf of, in this case, just half mv squared, except it's going to be mu dot of t squared dt. Now my EL equations, keep saying equations, but of course it's just one equation in this case, is going to be what? Well, mu double dot of t is equal to 0. Here I've combined the step of taking the first derivative with respect to u dot and then taking a t derivative of that. So we just get the same thing as up here. But this means that we get the trajectory for a free particle. All right, let's just keep going. What about t of v is equal to 1 half mv squared, and u of x is equal to mgx? So now we're thinking of an object which is experiencing a gravitational force. I've put that gravitational force in the x direction just to keep my variables the same. L of x and v, once again, is t of v minus u of x. I get s of u is equal to the integral from ti to tf of 1 half mv, sorry, I keep making that mistake, 1 half mu dot of t squared minus mg u of t dt. All right, it's getting a little bit old now, but let me do the EL equation for this. When I take the time derivative of the derivative with respect to u dot, once again, I'll just get mu double dot. Maybe you're starting to see a pattern here. On the other side, I'm going to get just the ordinary derivative with respect to u, but that's minus mg. So this is constant acceleration due to gravity. Okay, before I go on to another set of examples that are a bit more instructive, let's just give a couple of names to things. L is called the Lagrangian function, or usually just the Lagrangian. S, the functional, is called the action, or sometimes the action functional. And so what we're doing is finding curves that make the action stationary. trying to solve for trajectories in this way is called Hamilton's principle, or the idea that a physical trajectory should be one that minimizes the action, I should say, or makes the action stationary, is called Hamilton's principle. All right, now let's hop to a couple more exotic examples, just to see if we can take this all the way home and really replace the whole Newtonian theory with this kind of approach. And maybe replace is a bad way to term it, but just redo Newtonian theory in this new approach. All right, so the first more exotic thing that we can do is do examples that are not just in one dimension. Maybe the simplest one I can think of is, let's take a fixed positive charge at the origin. So Q plus Q fixed at origin. And in its vicinity, we'll place a charge minus Q. All right, we know exactly what the kinetic and potential energies are for this problem. The kinetic energy is going to be 1/2 mv squared, where now v squared is understood as the vector dot product. So actually, let me write it as v dot v for the time being. U of r, well, you'll remember this from an introductory electromagnetism class, is going to be minus kq squared over r magnitude. This k, by the way, is the Coulomb constant, not a spring constant. All right, so let's see if we can just stick this into our action and if it works out as expected. Once again, I'll let the trajectory that we're actually testing be u. I'll say that our action is defined by an integral from t initial to t final of t minus u. So that's going to be 1/2 mv dot v minus u, but this minus sign cancels the minus sign implicit in L, and so we get plus kq squared over magnitude of u. And where I've put v here, I kind of screwed up. This should be u dot dot u dot. At this point, I'm suppressing the argument t, but that's all right. It's still there. I just want to save a little bit of space. Okay, let's take our derivatives. And maybe just because we want to be careful, we'll take them relatively slowly. So the jth Euler-Lagrange equation, remember that when we have a curve in more than one dimension, we'll have as many Euler-Lagrange equations as dimensions. The jth Euler-Lagrange equation is going to be given by dl duj is equal to d dt of dl duj dot. We discussed that in our video on calculus of variations. Okay, so let's do these two terms carefully and separately. dl duj, well, here we're going to need to re-express this term in components. So the kq squared doesn't change, but in the denominator, we're going to have the square root of ux squared plus uy squared plus uz squared. Okay. Or I can think of all of this stuff to the minus 1/2. I think that's actually the easiest way. So I'm going to be able to pull my kq squared out. That's just constants. Then I'll get a minus 1/2 from the fact that this is all raised to the minus 1/2 power. Then ux squared plus uy squared plus uz squared, to the minus 3/2. And then from the chain rule, I'll pick out whichever of these matches j. So I'll get a 2uj. Okay, let's clean that up. The 2's will cancel. And then this thing in here is exactly u squared. So when we clean everything up completely, I'll get kq squared uj over uj cubed. And not uj, sorry, u cubed. U magnitude. Good. Now for dl duj dot, that we can get by rewriting this dot product. This is just ux dot squared plus uy dot squared plus uz dot squared. So this, in the end, is just going to be m times uj dot. That's relatively simple to check. That implies that d dt of dl duj dot is equal to, well, muj double dot. Good. Okay, let's set this equation up. So the Euler-Lagrange equation, the jth one, is just going to tell us that muj double dot is equal to, oh, and I forgot my minus sign from right here, is equal to minus kq squared uj over u magnitude cubed. Now, if I want to re-express that as a vector equation, I can do that in this case. This implies that m times u double dot is equal to minus kq squared over magnitude of u cubed times u. And this, in fact, is the equation for a charge, a negative charge, in the vicinity of a positive charge. So we don't need to change anything to be able to deal with this case in 3 dimensions. That's pretty cool. Now for the next example, I want to deal with a charge, a positive charge, plus Q, in the vicinity of a time-dependent electric field. So E is dependent on T. And let's say that this electric field is time-dependent but uniform. Great. So how do we get it? Well, we know from E and M that, oh, and I got to switch to my classical mechanics vector convention, even though I'm doing E and M stuff. So how do I get this? I know that E of t can be expressed as the negative gradient of a potential. And based on the fact that E is uniform, I can get that the potential ought to just be minus the E vector dot the R, the direction that it's going. Now, just for simplicity, let me put E in the Z direction so that I can just say that V, which is not a vector, sorry about that, is the magnitude of E times Z. Good. And that implies that the potential energy is given, so U of R and T. Just to be clear, this E does depend on T. Okay, the potential energy is given by minus Q E of T times Z. Good. All right, let's see what happens in this case. So I still have that T, which is just a function of V, still in 3 dimensions, is 1/2 mv dot V. I now have my U. I'll just copy it from above. And I want to stick these together and see what I get. So in this case, my S of U, which is equal to the integral from Ti to Tf of the Lagrangian is equal to the integral from Ti to Tf of 1/2 mv, U dot U dot, plus, because of this minus sign, Q E of T times U sub Z. Good, dt. Now, u and u dot also depend on t, but I've explicitly placed the dependence in here. Great. Does this work? Well, the first term is the same as before. So for my d dt of dl du dot in the jth direction, I'm still going to get muj double dot. But what about for dl duj? Well, in this case, I'll get 0 if j is not equal to z, and I'll get dl duz is equal to q e of t. Okay. So for my first two, for x and y, I'll get that muj double dot, I should say j is equal to x or y. I'll get muj double dot is equal to 0. In other words, it experiences no force in the y or j directions. But for j equals z, I'll get muz double dot is equal to q e of t. This is exactly what I expect. Since we know the force on an object, on a charge I should say, at time t is just equal to q times e of t. Great. So time-dependent potentials work just as well, and this is pretty interesting. Now, the next thing is the first case that's going to break us out of our mold. So far, I've said that L is just T minus U, but it turns out that that's almost always the case in this course, but not quite always. So if we have a magnetic field and a charge in that field, we need to say L is equal to T of V plus some M of both R and V minus, this is a V by the way, minus U of R. I guess U could depend on T as well. But let's just think about this particular case. So think about a charge in constant electric and magnetic fields. Okay, we know what to do about T and U. So T can be equal to half mv dot v, just as always. U of R. Now, the only thing that has potential energy is the electric field. This is important. The magnetic field, in that it does no work, does not cause a potential energy. Everything about the magnetic field is going to get encoded in M. Okay, so when we write U down, well, it's just going to be the exact same thing that we just did. Minus Q E dot R. Okay, good. Now, what is M? This is sort of a strange one. M depends on both R and V, and it's given by Q times V dot A, where A is the magnetic vector potential. Now, hopefully this is an object that you've encountered somewhere, but if it isn't, that's all right. A is any vector field satisfying B is equal to the curl of A. So we have a constant magnetic field. It turns out that there are actually quite a few different conventions, which are called gauges, that we could use for A. In other words, many different A's that lead to the same B. For simplicity, let's let B point in the Z direction. Okay, if B points in the Z direction, then one thing that we can do is let A we can let A be Q times X times B, which is just the magnitude, in the Y direction. Let's check and make sure that this works. So the Z component of the curl is going to be given by partial X of a Y minus partial Y of AX. Partial X of AY is all that we get and is exactly QB. So it checks out. And A can be X times B. The Q gets added in here. My mistake. Okay, great. So now we can write down our action for a trajectory U, which is the integral from Ti to Tf of T plus M minus U. Okay, so 1/2 mu dot U dot plus QU dot X B Y hat. And X is UX, sorry. Minus Q, but minus, so plus Q E dot U dt. Good. Now things get more interesting in this case, right? Because when we take our time derivative, our velocity derivative, dl u dot j, what do we get? Well, we get exactly what we had before, which is muj dot, but we get something else too. Let's write out this vector. This only gives us something non-zero when we're talking about the y component. So this is going to give us just this whole term, q times u dot y times ux times b. Good. So we're going to get something kind of interesting. This only gives us something non-zero when j is equal to y. We can use the Kronecker delta to express that. So I'll say when j is equal to y, we get something non-zero. And the something that we get is qux b. Great. Now, dl du j is what? Well, in this case, we're only going to get something from the third term, unless j is x, in which case we'll get something from this term as well. Okay, so let's do that. We'll have our Kronecker delta jx first. Then if j is x, we'll get QUY dot times b. And then if j is anything, we'll always get QE in the j direction. Great. Now I'll need to take these two. I'll take a time derivative of the first one as I'm writing the Euler-Lagrange equation. This is the jth one. Okay, what I get is mu uj dot plus Kronecker delta jy q uxb is equal to the Kronecker delta. Oh, and I didn't take my derivatives as I said I would. So I'm going to get uj double dot, and then here I'll get ux single dot. Good. Anyway, Kronecker delta jx q uy dot b plus qej. Okay, now let's see what this gives us for the force by taking only muj on the left-hand side. So this tells us that muj double dot is equal to delta jx q uy dot b minus delta jy q ux dot b plus qej. Now, you'll have to go and check this by yourself, but it's not too hard to show that this is the Lorentz force law. Which, if I write it in vector form, recall, tells me that mu double dot should be given by q v cross b plus qe. Awesome. So we can handle a whole wide array of things. We can handle 3D, no problem. We can handle time-dependent potentials. We can even handle magnetic fields. There's one more thing that I want to deal with before I go back to the light board, which is systems with more than one particle. So this is example 7. Kind of lost count at some point. Example 4, example 5, example 6. Yes, indeed, example 7. Okay, let's deal with two particles, masses m1 and m2, which are connected by a spring. So this is an interesting one. Now, our intuition tells us we'll only need T and U. We only need that M term if we're dealing with magnetic fields, in this course at least. And the T that we're going to get here will depend now on both V1 and V2. In particular, it'll just be a sum of T1 of V1 and T2 of V2. We know that that's how kinetic energy works. Kinetic energy is additive over systems of particles. That's the same almost for U. Every pair will have a potential energy that adds. But in this case, we only have one pair. We already discussed in the lecture on energy that we'll get one potential energy that depends on R1 and R2. Great. So what are these? Well, T of V1 and V2 is just going to be 1/2 mv1 dot v1 plus 1/2 mv2 dot v2, no problem there. And then U, well, it depends on the length of the spring. We'll say this has spring constant K and equilibrium length 0. But U of R1 and R2 is equal to 1/2 times K times the length of the spring squared. The length of the spring is R1 minus R2, and then I'll take that norm squared. Good. All right, so now my S, rather than just taking in a single trajectory, it needs to take in two trajectories. Now I want to make one conceptual thing clear. Taking in two trajectories in R3 is like taking in one trajectory in R6. In a certain sense, there's nothing different between, this system is the same as a sort of strange other system that lives in 6 dimensions rather than 3. So I'm going to write it like this with U1 and U2 separate, but you could think of it as being a single vector. And that means that all of the calculus of variations techniques that we've developed so far are still totally applicable. We don't have to develop a separate theory of functionals of two functions. All right, So anyway, I'm going to go from Ti to Tf in my integral. My Lagrangian is going to be T minus U. So I'll get 1/2 mv1 dot v1 plus 1/2 mv, and I've done this almost every single time. So it'll be u1 dot u1 dot 1/2 mv u2 dot u2 dot minus 1/2 k u1 minus u2 modulus squared dt. Okay, I'm also going to write this in a slightly different way because it's going to make what I do later easier. This is going to be u1 dot u1 minus 2 u1 dot u2 plus u2 dot u2. Excellent. Okay, now we're going to have 6 Euler-Lagrange equations. Let's do the Euler-Lagrange equation for particle I and coordinate j. So I'll get dl, duij. So in uij, I is the object, 1 or 2, and j is the coordinate. All right, so this derivative is only going to know about these, this term here. Okay, now if, for instance, I is 1, then I will see a term in here and a term in here. I'll leave you to work out the details. We're going to get the minus 1/2 k pulled out. Then, from actually taking the derivatives inside, we're going to get 2 uij, and then minus ui plus 1 times 2 from the 2 here, times, ui plus 1 comma j, where I plus 1 is the other one. I could say it's, understood mod 2 or something like that, but it's just whichever particle is the other one. Good. dl du dot ij. Well, just as before, I'm just going to get m times uij dot. And taking these two together, I can now write down my Euler-Lagrange equations. I'm going to get m uij double dot, once I take this time derivative, is equal to, well, the 2's cancel, so I'm going to get minus k times uij minus ui plus 1 j, which is exactly Newton's second law for two masses attached by springs. Now, I can grind through many, many more of these examples, but I haven't sort of demonstrated something really essential for you. In all of these examples, I've been able to take some complicated machinery and use calculus of variations to find a particular action functional such that when I when I find the Euler-Lagrange equations for this functional, what I get is the same equation that I would get from Newton's second law. So in other words, I can find functionals that give me back the equations of motion that I expect. But we already know how to get equations of motion for all of the systems that I dealt with. In a certain sense, I just told you a really complicated way to get something that you already know. So what is the point of this technique in the first place? I need to give you some sort of value add that this gives you above what you could do before. That's what I'm going to do right now, but I'm going to hop back to the light board to do it.
Okay, before we can go on and do any more examples, any more complicated examples, I should give you the theory of what's going on here. All right, so for almost all the examples that we've just worked, I'm going to disregard the magnetism one for just a moment here. We've been able to define the Lagrangian, this function, on x, or actually let me say on r, so that we can be in any dimension we want, on r and v by t of v minus u of r. And let's see why this works as the integrand for our functional. So I'll say s of u is equal to the integral from ti to tf of l u dot t. In this case, we're actually dealing with things that are time independent. I'll keep it like that for the time being, just for simplicity's sake, but it generalizes relatively easily. Okay, dt. And now let's rewrite that using the form that we actually have here. Okay, so this will be the integral from ti to tf of t of u dot minus u of u vector, let me say, dt. Okay, now all we need to do is find the Euler-Lagrange equations. So we'll start that by finding the partial of the Lagrangian with respect to u sub j. Okay. Well, the Lagrangian only depends on u sub j in terms of this u, the potential energy. So this is going to be the derivative of the potential energy. Let me maybe write this on as a fraction. And then this minus sign needs to get pulled down. That's important. The derivative of the potential energy with respect to u sub j. But actually, let me suggestively rewrite this as the derivative of the potential energy with respect to r sub j evaluated at r sub j is equal to u sub j of t. Okay, good. Next, we need to do the derivative with respect to uj dot. Good. Well, in this case, we just are taking the derivative with respect to this kinetic energy part. Now, for a system written in Cartesian coordinates, we actually even know what this object is. It's 1/2 m u dot dot u dot. Okay, so now let's write that term or that form in here. This is going to give us, by using the product rule, for instance, m times u dot. But that implies that the, oh, and this shouldn't be with respect to uj at this stage, or I should say this is with respect to uj, so this should be muj dot. Okay, so that means that the time derivative of this thing is equal to muj double dot. Great. Now let's bring these two facts together. What we get is that muj double dot is equal to minus the partial with respect to rj of u evaluated at rj is equal to uj. Okay, now this is a vector equation, really, in disguise, in that I can combine all of these components. However, when I make the vector in rectangular coordinates that involves all of the partial derivatives, well, that is the gradient. So by definition, what I get here is mu double dot is equal to minus the gradient of u evaluated at uj. But this is Newton's second law. Because remember that the negative derivative of the negative gradient of the potential energy is exactly the force at u sub j. Or sorry, at u. And I noticed another mistake here. I need to evaluate all the rj's at u sub j for the respective j's, so I can write that as r is equal to u. Good. Okay, so that's fine. This is actually pretty cool, right? It turns out that we can use this new functional calculus stuff to rederive Newton's second law. But if that's all that there was here, I think that calculus of variations would not be such a potent tool within the arsenal of someone studying classical mechanics. Instead, the thing that makes this really, really useful is that we can use it not only for systems which are moving around in Rn. Oftentimes in physics, we want to treat systems which are in some way constrained. And those constraints make Newtonian mechanics really challenging because the constraints come from constraining forces. So in the process of trying to figure out the trajectory, we're also always trying to figure out what strength the constraining forces need to be to constrain the object to the path that it needs to follow. However, we'll see that in Lagrangian mechanics, that isn't true. I'm going to erase the board and then we'll get right to it. All right, I'm a little worried about getting too abstract in this next section on constraints. So we're going to work out the theory, and at the same time, step by step, we're going to work out an example that demonstrates what I'm talking about. So first of all, we have to talk about different kinds of constraints that we might have a classical object experience. The simplest kind of constraint is called a holonomic constraint, and that's the kind that I'm going to deal with here. Oops, constraint. So let's say that this system lives in Rn. I want to find a function k on Rn such that k of r is equal to 0. Now this may seem a little bit of a funny way to define a constraint. A constraint I would normally think of as some sort of path or some part of space that the object is bound to stay on. But it turns out that this formulation will always work for holonomic constraints. All right, so let's hop over to our example and we'll see how this works. We'll do maybe the most sort of textbook example that we can and deal with a particle that's sliding frictionlessly down a ramp. Okay, so here are my x and y axes. And we'll say that the particle starts at the origin and slides down this ramp. So here's my object at time 0. It has mass m. Oops. And this ramp forms an angle theta with the horizontal. Okay. Now, if this is the point where I've reached in my trajectory at some time, x, y, then I definitely can come up with an equation like this, k of r. So what must always be true of this object sliding down the ramp? Well, it always lies on this line. The equation for this line is y is equal to minus the tangent of theta times x, which you can check yourself. Okay, theta here is a constant, by the way. I want to make sure that that's very clear. So what could I take as my k function? Well, I could take k, which takes r, which is x and y in this example. And I can just move the tan theta to the other side. So it's y plus tan theta x. And this is always equal to 0 for points on this line. Good. Okay, now if I have a holonomic constraint, it turns out that I have a constraint subspace. So there exists a constraint subspace. Let me say U. Maybe I don't like U. How about C, which is a subset of Rn that has at least one fewer dimension. Okay, so this problem is going on in R2. My constraint subspace is exactly the points on the line. So C is exactly equal to the line above. Yeah, maybe square brackets are more appropriate here. All right. Now, anytime we have another subspace, I can use some parameterization of that subspace, whatever parameterization that I want. So can parameterize C by S1 up to Sm, where m is less than n. Okay. In this case, the line is one-dimensional. So I only need one coordinate to parameterize it. In this case, the thing that makes the most sense is just the length that we've traveled. Okay, so for our example, let me use some of this space over here, and let's write x and y in terms of s. So we have x is equal to, well, that's going to be s times cos theta. And y is equal to, well, that's going to be minus s sine theta. And while I'm at it, let me take the derivatives of these things with respect to time as well, noting again that theta is constant. So these imply that x dot is equal to s dot cos theta, and y dot is equal to minus s dot sine theta. Great. Okay, now is the rub. So we've gotten our subspace, constraint subspace C parameterized in some new set of coordinates. I can now define a new action. Let me call the original action S. So original action S acting on R1 through Rn. And maybe I should call this, I want to think about trajectories. So I'll say U1 through Un. So each uj is a function from R to Rn. And I'm going to define a new action, sigma tilde, acting on U tilde 1 through U tilde m, which is a trajectory in S space. So in other words, it's a trajectory through these S coordinates. Now, because this constraint subspace is a subset of Rn, we have some map gamma from C to Rn. So let me squeeze that in here. So gamma is a map from C to Rn. Mathematicians would call this map an inclusion map, but whatever. It's just the statement that this line, for instance, lives in R2. It is some subset of R2, and I can think of it abstractly as a line parameterized by one coordinate, but I can also think of a map that sticks it into R2. So in other words, it's my map from S to the tuple S cos theta minus S sine theta. Okay, maybe it's good to write that down. So here, gamma of S is equal to S cos theta minus S sine theta. Good. All right. So now, how do I define this S tilde? Well, I want it to act on these things, but I only have naturally an action S that acts on these things. Well, what I can do is define S tilde by S tilde acting on U1 tilde through UM tilde is equal to, by definition, S acting on gamma of U1 tilde through UM tilde. All right, so now I have some new action. And let's actually write out what that action is. So this is equal to the integral from Ti to Tf of the Lagrangian evaluated at gamma of U1 tilde through UM tilde. Then the derivative with respect to time of that exact same object. And then possibly t dt. Great. And now, rather than trying to find a stationary function of this original s, we can find a stationary function of this s tilde. Now, why does this all work? What is going on here? Well, the key is that the Lagrangian, even though my system is constrained, has not changed. That's because the Lagrangian is equal to t minus u. In other words, the Lagrangian depends on the kinetic energy of the system and the potential energy of the system. The key here is that constraint forces do no work. Let me put some stars next to this because it's so important. It's the whole reason that this technique is so powerful. Constraint forces do no work, and so they don't change either T or U. We get to keep the kinetic energy and the potential energy. The only thing we need to do is reparameterize our system using coordinates like S. These coordinates, by the way, are given the name generalized coordinates. All right. Now we've done a lot here on the theory side. Let's keep going on our example side. Okay, so S for this system is the integral from, and I should say S of U, sorry, where U is a 2D vector. Anyway, S from T is the integral from Ti to Tf of 1/2 m u dot u dot, let's say, and then minus m g u y, right? Because mgy in general is our potential energy. And we stick the minus sign there always in the Lagrangian. Okay, so how do I write S tilde? Well, I'll be honest with you. Most people wouldn't. They would just start plugging in these gammas of the U tildes. So how do I do that? Really, you should think of gamma as an instruction to rewrite S in generalized coordinates. So all I need to do is start plugging in what I have up here, okay? So this tells me that S tilde, I'll use that notation here, although again, most books wouldn't, of S, which is now an action depending on a single trajectory, Actually, let's, instead of using s, which I guess we would think of as any length, we can use u tilde. Okay, so s tilde of u tilde is equal to the integral from ti to tf of half m. Okay, now I need to replace u dot. U dot is the vector x dot y dot. Okay, so let me do that replacement. So first I have u tilde dot cos theta. Next I have u tilde, minus u tilde dot sine theta. And then I have this vector squared. Okay, I'm just going to use the squared here to save a little bit of space rather than the dot product with itself. Then I have minus mg uy. Uy is going to get replaced by, so I'll have a plus because of this minus sign. Mg stays the same. And then u tilde sine theta. Great. Okay, let's write this out by squaring this first term and then adding it to this second term. But by the Pythagorean identity, I'll have a cosine squared in the first part and a sine squared in the bottom part. So this is equal to the integral from ti to tf of 1/2 m u tilde dot squared, where this is now just a number, and dt, forgot, plus mg u tilde sine theta dt. Okay, let's squeeze in our Euler-Lagrange equations down here. So dl du tilde is equal to, well, that's going to be just mg sine theta. Meanwhile, d dt dl du tilde dot is going to be equal to, well, just this part would give me m u tilde dot, where the 2 up here has canceled the 1/2. And then I take another derivative and I get m u tilde double dot. So in other words, the Euler-Lagrange equation is m u tilde double dot is equal to mg sine theta. But that exactly tells me that I expect the object to accelerate down the ramp with its u tilde coordinate accelerating at an acceleration that isn't g, but is g times the sine of theta, which is exactly what you would have gotten doing this with normal forces in an introductory mechanics class. Okay, so the point here is that holonomic constraints are really super helpful to us. They tell us that we can deal with systems using generalized coordinates rather than other coordinates, and in the Lagrangian formulation, that's the only change that we need to make. Now, there are some constraints which are not holonomic, and that can be really challenging to deal with. A great example is given any time we have a rigid body. So for instance, if we have a ball. Now it turns out that if I have a ball and I draw a little dot on it, and I roll my ball so that I've rolled it far enough that the dot appears on top once again, well, if I come to this same point by some other path, I'm not guaranteed that by that other path, the ball will have, maybe I should have done this one in a different color. I'm not guaranteed that by this second path, the dot will be on top of the ball. Go ahead, try it. It's not very hard to find a path such that the ball's dot appears somewhere else, even though it ends up at the same location. And that means that I can't write a holonomic constraint for this kind of system. So unfortunately, one of the most common types of systems, rigid objects rolling around on things, are not governed by holonomic constraints. But that doesn't mean that there aren't a lot of systems that are. And in fact, we'll get quite a lot of mileage out of this technique as we keep going. I'm going to hop back to the computer to give you a couple of new examples of systems that are undergoing holonomic constraints. I'll see you there.
So let's see how this works in practice. Remember that the whole goal is to write down kinetic and potential energies, just like we've done before, while ignoring all forces of constraint, just completely leaving them out of the problem. and writing things down in whatever coordinate system is sort of the simplest for what I want to do. So the problem that I want to deal with is a familiar one. Let's just deal with a pendulum. We'll say that the pendulum has length L and mass M. Now, I can write down T of V, which is 1/2 mv dot V for this 2D problem. And U of R is just mgy. I'll let this be the y direction and this be the x direction. Actually, let me do something a little bit funky. I'll let downward be the x direction and to the right be the y direction. This seems really strange, but it will make sense later. But it does change my potential energy, which is now minus mgx. Okay, so why am I writing this, but also sort of indicating that I could do something else? The answer is that this problem, while it is 2D, is constrained to one-dimensional motion. The only place that the pendulum can move is on this circle of radius L. So I might as well parameterize it by something else. So let me use the angle theta that this makes with the vertical. Now you see why I've oriented my x-axis in this strange way. I can now use polar coordinates with my r coordinate fixed at the value of L. Okay. So what I should do is take my trajectory and use polar coordinates and unit vectors to write it. So my trajectory will be u, but I know that rather than being just, rather than being at any r, this is at an r value of L in the r hat direction. Good? Next, I need u dot. And for that, I need to do what I've done several times before and take a derivative of the r hat vector. But you can go back and look at how that works, r hat dot. What I get in the end is going to be L times phi dot. Oh, and yeah, let's, instead of theta, let's use the same notation as our textbook Taylor and use phi instead. Okay, L phi dot in the phi hat direction. Now let's use that result and square this. So u dot dot u dot is equal to L squared phi dot squared, and then phi hat dot phi hat is 1. It's a unit vector, and so its dot product with itself is 1. Great. Okay, we're now ready to write down our action. S of u is going to be equal to, well, it'll be the integral from ti to tf of 1/2 m. V dot v is going to get replaced with L squared phi dot squared. Now minus mgx, that's just, x is just this length, which is L times the cosine of phi. Okay? But then this minus sign here means that this would become plus mgx, and x is L cos phi dt. Now, the amazing thing about this is that even though this had been an action functional of u, I can replace it with just phi. So this is really important. It's subtle, but really necessary to realize what's going on here. Rather than putting in that s is a functional that takes functions from R2 to R, so u would take R2 to R. S is now a functional that eats functions from R to R. So the functional doesn't eat functions from the, oh, sorry, U is not R2 to R to R2. Phi is still R to R. In any case, U is not a functional that eats functions into Rn if we're in n-dimensional space. It's a functional that eats functions into the number of coordinates needed to describe our system. These are called generalized coordinates, and we'll get a chance to discuss them more later on. Okay, so we get to cross out U and have this just be a functional of phi. That means we only need one Euler-Lagrange equation. dl d phi, in this case, is going to be minus mgl sine phi. dl d phi dot. We have to do a little bit of work here, but what we're going to get is 1/2 times ml squared times 2 phi dot, which is just ml squared phi dot. So our Euler-Lagrange equations, after taking a time derivative of the second equation, is ml squared phi double dot is equal to minus mgl sine of phi, which is indeed the equation of motion for a pendulum. Okay, now we can take this generalized coordinates notion to its logical extreme. Rather than dealing with the number of degrees in which our problem actually lives, or the number of degrees of freedom in which our problem actually lives, we only need to deal with the number of degrees of freedom in which it isn't constrained. So let's deal with kind of a fun example. What if we had an object that's in some sort of a parabolic well, and it can't go through the surface and it can't bounce off of the surface. It's just stuck on the surface, but it's otherwise under the influence only of gravity. So we'll make this the z direction, and these can be the x and y directions, but let's work in cylindrical coordinates instead of Cartesian coordinates. Okay, so we'll let this surface have equation z is equal to rho squared over a, where a is a length, rho is our cylindrical radial parameter, or radial coordinate. This is notation from the textbook, Taylor. Great. Okay, so this problem lives in 3 dimensions, but how many dimensions do I actually need to describe the motion? I only need 2 generalized coordinates. That's because if I know the x and y positions of this system, or equivalently, if I know the rho and phi coordinates of this system, then I know the z coordinate because this thing is stuck on this surface. Great. So let me write down t once again. And in this case, it's going to make sense to write it down in cylindrical coordinates. So I get to use some of my results from before, just like I did up here. Okay, so I get 1/2 mv dot v. But let's remember that if our trajectory is u, then u is going to equal the u radial coordinate, which I'll call just u with no underline, in the rho hat direction, plus uz in the z hat direction. Okay. Now, that implies that u dot will be equal to what? It will be u dot times the rho hat vector plus u times the rho hat vector dot. But that's just like the r hat vector dot in polar from above, which we see is given by phi dot phi hat. So phi dot, I'm going to have to give this some specific name that tells us that we're dealing with our trajectory in specific. Let me use psi dot. So here we go. Our trajectory's coordinates can be rho equals u, phi equals psi, and z equals uz. Not the perfect notational convention, but it's good enough for now. Okay, so anyway, this times phi hat, and then plus uz dot z hat. Okay, so in our coordinates, once I do the dot product, I'm going to get u dot squared plus u squared psi dot squared plus uz dot squared. Great. Okay, now for u, this is where things start to get really interesting. U of r is equal to what? Well, it's equal to... and before I go on, actually, I want to be a little careful here. This is what T of V is. So maybe this, I should say that this implies that T of U dot is equal to this. Great. Okay, so in any case, U of R, we can do kind of the same strategy. That's mgz. Fine. So what's U of U vector? Well, it's mguz. But in both of these cases, I want to take this uz and get rid of it, because I know what uz is in terms of my other coordinates. uz is equal to u squared over a. Good. So I need to work this out. This thing is d dt of u squared over a. Remember, u squared is a function from time into this position. So what do I get here? And sorry, not u squared over a, u to the fourth over a squared. This is going to give me 4u cubed over a squared times u dot. Good. Meanwhile, down here, it's slightly simpler. This is just exactly u squared over a. Okay. So now I have my action, but I should write it just as a function of my generalized coordinates. A functional of my generalized coordinates, sorry. My generalized coordinates are u and psi. And so I get this integral from ti to tf, just as always, of 1/2 m times u dot squared plus u squared psi dot squared plus 4u cubed u dot over a squared. Great. Then I need to do minus mgz, but that's minus mg u squared over a. Okay, and then dt. Good. Now, I'm going to go ahead and do the Euler-Lagrange equations. But really, the main thing that I wanted to show you was just this, that you can use generalized coordinates to write down a whole bunch of things. The key is just that the forces of constraint, which would have been really hard to deal with in Newtonian mechanics, we would have had to be figuring out normal vectors and the magnitude of normal forces and things like that. They're simple to deal with in this formalism. And it all comes down to the fact that because those forces of constraint aren't doing work, we don't need to account for them in a system that deals with energy in the way that this Lagrangian mechanics approach does. Okay, just for practice, let's finish getting the Euler-Lagrange equations. So we're going to need to get one for u and one for psi. Let me just do those separately in this case. So dl du is going to be equal to, well, we get one from this term. That's going to give us mu psi dot squared. We get another from this term. The 4 cancels the 2 down to a 2. Then I'm going to multiply that 2 with a 3 to give me a 6 m u squared u dot over a squared. Then I get a minus sign. So this 2 here cancels with a 2 over here, or the half here. So we get minus m. Oh, and there's this doesn't multiply that half, sorry. Minus 2 m g u over a. Great. Okay, now dl du dot is equal to mu dot is the first term. Next, I get something from this. So here I'm going to get 2 mu cubed over a squared. And now let me get my Euler-Lagrange equation from these. So I need to take a time derivative of this, right? So I'll get mu double dot plus 6 mu squared u dot over a squared. Looks good to me. And that is equal to mu psi dot squared, good, plus 6 mu squared u dot over a squared minus 2 m g u over a. Okay, now how about the psi equations? So dl d psi is equal to what? It's equal to 0. Now we'll get to talk more about this in the next set of videos, but I want you to notice that when dl d psi is equal to 0, or the dl with respect to, or the derivative of L with respect to any of the generalized coordinates is equal to 0, it means that the derivative of L with respect to the derivative of that generalized coordinate is constant, because it's going to give me the Euler-Lagrange equation, dl d psi dot, that d dt, is equal to 0. So dl d psi dot is equal to a constant. And this is super important. In this case, the reason that dl d psi is equal to 0 is precisely because neither my potential nor kinetic energy depends on the angle that I am, or that I have, around this parabolic object. Paraboloid, I think, is the name. And that is super interesting, right? Because I have this symmetry about this object, I get some sort of constant of the motion. Again, we'll come back to this notion later. I just wanted to point it out here. Okay, in any case, let's finish this up. So this is my term that depends on psi dot squared. So I'm going to get dl d psi dot is equal to mu squared psi dot. So my Euler-Lagrange equation is m times, 2m u dot psi dot plus mu squared psi double dot is equal to a constant. Sorry, is equal to 0, or mu squared psi dot is equal to a constant. Great. Now, this is a case where the equation of motion itself is extremely hard to solve. I mean, I have no idea how I would go about trying to solve this equation for u. But what's amazing is that this equation is correct. And once we have an equation that's correct, even if there aren't analytic methods to solve it, there may be numerical methods to solve it. And there may be ways other than solving it to get intuition about what its solution looks like. So there's a lot to be gained from looking at the Lagrangian formulation. And the Lagrangian formulation historically kicked off a whole bunch of new physics throughout the second half of the 18th century. Anyway, thanks for watching this one, and I hope to see you in the next video.